Good afternoon. I think we will quickly recap what we were doing earlier and then go to the burn rate of composite propellants and also address ourselves, are there some particular values of n, the exponent in burn rate law R is equal to APN, which is necessary when we design these solid propellant rockets. What we did in the last class was we told ourselves this is the propellant grain which is there inside a particular case, this is the nozzle, we ignite the surface of the propellant, the surface regresses at a particular rate which we call as the burn rate. And what did we do for the case of double base propellants? We told ourselves we have nitrocellulose and nitroglycerine, we had NO2 aldehydes and also some other constituents here which react, take the temperature from the surface temperature to the temperature at the edge of the fizz zone, this was the foam zone which is a preheated solid surface of the propellant, and then you had the fizz zone where the temperature went to T1. Thereafter it remained constant at this value in the dark zone, wherein essentially the reactions between NO and NH2, NO and CO do not generate much heat, but thereafter the reactions generate heat and you get CO2, CO, H2O and all, and in this case the temperature went to the final value. This zone, this particular zone of dark zone is there only for pressures less than around 10 MPa or 100 atmospheres, and at higher values what we got was the temperature directly goes to the value of Tf. Having said that, we wanted to translate this into the burn rate, and therefore we again looked at the preheated zone, a foam zone, a fizz zone, a dark zone and a luminous zone. We wrote the equations in this particular zone, and what did we write it as? We took a small element in the fizz zone, this was at x is equal to 0, the fizz zone extended up to x is equal to L. Mind you, the length of these zones are fraction of an mm thick, we just extended it to be able to do all this. We had a small element here with unit surface area, and we said Qx enters, heat enters, heat leaves, the heat leaving is in excess by this amount, and the enthalpy, that is the rate, mass generation rate, is equal to rho g into Ug into specific heat into temperature. It leaves at a temperature T plus dt, and therefore this is equal to the excess heat transfer and the heat generated by the chemical propellants, and we were able to write the equation, and based on this equation we said we could get the temperature profiles for given values of Ug, Pg and rho g, right. Okay, let us get forward. We also found that in the zone wherein you have the dark zone, the variation of the logarithm of the burn rate versus logarithm of pressure was slightly less, because the temperature T1 which supplies heat to the surface is lower than when I had the final temperature directly supplying heat, and therefore I have low exponent here and a higher exponent over here. We would like to do the same type of analysis for a composite propellant, and a composite propellant is distinctly different from a double base propellant. What is the distinction? Let us put it on the board. We said AP in the form of crystals, and this AP is contained in the polybutadiene. We could also have aluminum, just like we saw in the sparkler. When there is metal, it is much hotter, and that is why aluminum is put. Therefore you have something like AP solid crystals, and in between maybe it is bonded by the polybutadiene, let us say p band, and this p band could either be HTPB or let us say p band, it could be some polybutadiene, it could be polybutadiene acrylic acid acrylonitrile, or it could be HTPB, it could be CTPB, this is the fuel or the binder. And when I supply heat and start making this burn, you know AP is NH4ClO4, right. It contains oxygen, it contains hydrogen, therefore I could get a flame, something like a monopropellant flame, this itself will burn. But the hydrocarbon which is over here, maybe the polybutadiene, cannot burn because it is just hydrogen and carbon, it does not contain oxygen. Therefore the volatiles of hydrogen and carbon come over here. Therefore let me use a slightly different color over here to show this. maybe this is the fuel vapor which is coming out, this is the fuel vapor which is coming out. This is a monopropellant flame, and this flame is typically at a temperature of around 1600 Kelvin. Maybe whenever we are talking of this combustion taking place, we presume that combustion takes place at a pressure of the order of greater than around 10 atmospheres, because we are not going to have rockets which have chamber pressure less than this. Therefore, we are talking of something like 1 MPa pressure, and at this pressure maybe I have the flame of AP which is coming over here, I have the vapor coming over here of this, and this is the picture I can draw in my mind of what takes place. Mind you, in practice when I look at the propellant, I will have AP, then AP here, I have AP here, I have small particles of AP here, I could have aluminum in between, I have small things. I am just magnifying this zone and separating it corresponding to this distance and putting this scheme to be able to formulate a model. I am interested in having a model which I can solve for writing an equation. Therefore, I have fuel vapor coming over here, I have oxidizer vapor which is terribly oxidizer rich, and when the fuel vapor meets over here, I could have something like a zone wherein I could have something like a zone over here wherein again burning will take place between the oxidizer rich flame which is coming from AP, and this will be something like mixing taking place or a mixing dominated combustion. Whereas over here it is just premixed, whatever AP is giving out as vapor it comes out this, therefore over here I have what I will call as premixed, there is no mixing involved. At the edges I transport the fuel here, I transport the oxidizer rich vapor here, when they meet they mix and burn, therefore we call this mixing dominated combustion as diffusion, essentially controlled by diffusion combustion, right. Therefore, above the vapor I have premixed combustion, at the edges wherein the vapor comes and meets these hot gases I have mixing dominated combustion, and the temperatures here are typically at these pressures greater than 10 atmospheres around something like 3200 Kelvin. Well, gases are still reacting, this is still oxidizer rich, some of these again products of combustion again meet over here, products from this come over here again meet it, therefore I have another mixing combustion here, and this is the final diffusion flame. And the temperature here is typically around 3500 Kelvin. Therefore, what is the picture I am trying to draw? I am trying to draw a picture wherein, or a model in my mind, a mind model wherein I have AP getting the oxidizer rich products which are essentially decomposition products which are premixed, they form a diffusion flame over here, the first diffusion flame, a diffusion flame over here. If I look over here I will again get a diffusion flame over here, I will again get a diffusion flame over here, well I will get a final flame over here, and therefore this flame and this flame are at 3200, this is around 1000 at odd Kelvin, and the highest temperature is reached over here. This could be my mental picture or model of combustion or burning taking place in a composite propellant. Well, this is distinctly different from what we had for the double base propellant, wherein we had maybe aldehydes, maybe NH2, NO coming over here, you had a fizz zone, you had a dark zone, you had the second luminous zone, whereas here I have a premix zone, a first diffusion and a second diffusion flame. Now, how do I solve this? It becomes a little bit erratic, right? It is becoming a little complicated because now I am talking in terms of a series of oxidizer particles over here. I have something like a premixed combustion taking place just above it, low temperature. I have something like a diffusion flame over here at the edges over here, maybe something like this, it could have been either way, and then I have a final diffusion. diffusion flame over here. Now, what is it I am talking of? I am telling, well, AP here, maybe the polybutadiene over here, AP over here, and this is what I expect. If I were to have AP of smaller particle sizes, maybe I have smaller APs over here, well, the zones will be something like this, and my final heat release zone will be nearer. In other words, it tells me that the final diffusion flame, because the length of this will be proportional to the size of AP, if AP size is less, that the final diffusion flame will be nearer. I will still have these diffusion flames over here, the premixed over here, and I could still have this. Therefore, AP size will decide the distance at which the final temperature will take place. Now, let us go through the same assumptions again. Let me assume that the final temperature of the combustion products is Tf, and now I want to make an assumption. How do I solve this? I cannot have all these particles and keep solving it. Therefore, why not make an assumption? I say, if this is my propellant surface, it is composite. I know the size of this is around 300 microns, the fine is around 30 microns, I cannot see that closely. Therefore, I have something like a distance of a centimeter or 2 centimeters or a meter. Now, I tell myself, well, the final diffusion flame formed is at a temperature Tf, and it is formed at some distance away, something like, let us say, x star, a standoff. It forms after some distance. Why does it form after some distance? Why does it not form at the surface? Well, I have the AP flame first which forms, then the mixing takes place, then the secondary mixing takes place, and then the final diffusion flames forms at some distance away. But this distance again is a fraction of an mm in practice. Just like in the sparkler, we thought that it is at the surface, but if I take a magnifying glass and see, well, there is a distance over here. Therefore, now I think I am in a position to write an equation for this. The final temperature is Tf. Well, this is the propellant surface over here. I am interested in writing an equation for the burn rate, so many meters per second. Now, this we can readily do. Let's look at this slide again. This is where I show I have 3 AP over here. I have the shaded portion, which is the monopropellant flame, that is the premixed flame, and then I have the vapor coming from these hydrocarbon. This is pure vapor. When it mixes with the oxidizer rich gases, I have a zone of diffusion flame over here, I have a zone of diffusion flame over here, and the products from this diffusion flame and this again meet and give me a final diffusion flame here, and the distance between this final diffusion flame and the surface is what we call as the standoff or the height x star. If this part is clear, I go to the next one. Well, it becomes quite simple now for me. I say this is my final zone, I have a standoff distance as x star, and this is my surface, and the surface temperature, which is Ts. Mind you, the propellant gets heated here from initial temperature to the surface temperature, and in this gas zone I say that the temperature varies between Ts to the final value. This is the mental model I have, that is the model for the combustion or burning of a propellant. At this point I thought I should illustrate what happens. So, many of you are working in combustion. These are the experiments which we were doing in the lab. I have something like butane gas coming over here, and when I ignite butane gas in an orifice, at the orifice itself I have a flame like this. I increase the velocity. Well, at the surface I do not have combustion, but it takes off after a certain distance. I have mixing taking place in this zone, and thereafter I have combustion, and still at a higher velocity. Well, I have this zone is the zone wherein mixing taking place, it is at high velocity, the heat is insufficient to propagate the flame into this. I have something like a standoff distance here. Well, the standoff distance is something on these lines, but not precisely because of velocity, but it takes a certain distance for the final diffusion flame to form. Therefore, I would like to write an equation for this. Let us write the equation. My equation is we have the surface here, we have the final diffusion flame over here, we have the propellant over here Tf, we have the surface temperature Ts, and we also found that if I were to plot the temperature distribution along this, that means this is my propellant here, I show this as temperature, this as the distance over here, in the depth of the propellant the temperature is the old value, that is the initial temperature, and then what happens near the surface the temperature increases to Ts at the surface, and then in the flame zone it further increases to something like Tf over here. Mind you, this is my increasing direction of T and this is the distance from the in depth propellant, wherein the depth of the propellant is still at the initial value. At the surface I have an increase in temperature Ts and it goes to the gas value. Therefore, now I want to know what is the heat which is coming on the surface. I am interested in finding the value of Kg dt by dx at the surface of the propellant, and this I can approximate it by saying that the temperature increases to Tf from the surface value over a distance, and if I say this distance is like something like a x star, I just use this word x star, I will give you the reason for using it, is equal to Kg into something like Tf minus T at the surface divided by x star. This is a very simple method. You know, there are various flame models which are used for describing the combustion of composite propellant, but this particular one was formulated by one Professor Hermans. He was at Waterloo University and it was very simple and is very illustrative. Therefore, I just use this. There are various models, we say granular diffusion or some flanks model, but I do not see anything more coming out of those models compared to this simple model. Well, this is the heat which is coming to the surface. I say this is equal to Q dot S. I consider unit surface area, therefore it is so much joules per second per meter square. This is the units of this over here. Mind you, A is unit surface area, and where does the heat go? The heat goes to increase the surface temperature from the initial value Ti to the Ts value. Therefore, what is it? Let us say that the rate at which the propellant regresses or burns is equal to m dot. Then what happens? The temperature, I have specific heat into it increases to the surface value from the initial value, plus some heat is also supplied. Suppose at the surface I have some endothermic reactions taking place because I have the binder, I have something like binder over here which I call as polybutadiene. It has to get heated, it has to supply the, it has to vaporize and all that. I need to supply this, therefore I say I need to supply some Q chemical to it, some endothermic reaction Q chemical, and therefore this heat goes to supply this, and therefore I can write my equation as thermal conductivity of the gas into the flame temperature minus the surface temperature of the propellant divided by the flame standoff is equal to the mass which is getting released at the surface into the density at the surface, no, into the specific heat of the surface, mass into specific heat into the surface temperature changes to Ts from the initial value Ti, plus I have heat which gets released at the surface, might be an endothermic reaction at the surface, Q dot chem, and therefore this gives me my energy balance equation. Namely, this is the heat which gets translated or transmitted from the flame to the surface, and this helps to increase the surface temperature to Ts from the initial value, and also supplies the energy required to vaporize the surface or to convert the surface from solid to vapor through a set of endothermic reactions. Therefore, now using this particular reaction, if I have to write the value of m dot is equal to the thermal conductivity of the gas region, then I have the flame temperature minus the surface temperature divided by the flame standoff distance divided by the specific heat into the surface temperature minus the initial temperature of the propellant plus the value of heat release due to chemical reactions at the surface. Actually, in this I need not even put dot here because it is just the magnitude of heat release, and therefore maybe I should do away with the dot here and just write Kg into Tf minus Ts by x star divided by C, that is the heat required plus the endothermic reactions at the surface which causes it. Now, I want to discuss this particular value of mass release, and the mass release at the surface can again be put, since I considered m dot, maybe I consider unit area over here, maybe I say m dot is equal to rho PR, or rather the burn rate can now be written as kg into Tf minus Ts divided by x star divided by m dot is equal to rho p into r, because you have so much meters per second, so much kilograms per meter cube, therefore I have density of the propellant coming over here into C into Ts minus Ts plus the value of Q chemical. Now, let us examine this equation under different conditions. I find that there is a flame which is standing off at a distance x star from the propellant surface, and the change of x star, let us again sketch it. We have seen this sketch several times during this class. We have the flame at a temperature Tf standing at a distance x star. Now, if the size of the ammonium perchlorate particle size is small, then the mixing will take place immediately near to the surface and the flame will be near. Point 1. If the chamber pressure, on the other hand, or if the pressure at which the burning rate is evaluated is high, if the pressure is high, you have more number of molecules which can react, and therefore the x star can come down. Therefore, what is the inference which we can draw? Well, if I have fine AP particles, fine ammonium perchlorate particles in the composite propellant, then it is quite possible that x star will be smaller and the burn rate will be higher, 0.1. If the value of pressure at which the burning takes place is somewhat higher or large, let us say, then chemical reactions get finished in a very short time, and therefore x star will be small, and if x star is small, well, the burn rate will be higher. Therefore, a higher value of chamber pressure also leads to a higher value of the burn rate R. Therefore, we are finding certain things. Maybe if the pressure is higher, the thermal conductivity of the gas will be higher, and therefore again burn rate will be higher. Again, rho p is the density of propellant does not change. Maybe the surface temperature effects will come in, maybe the endothermic reactions activation energy will come in, but something we are finding that pressure is a major factor, because pressure decides the value of x star, and therefore you remember when we did double base propellants, we could say that the burn rate law could be expressed as in terms of St. Robert's law as R is equal to AP to the power n. We find here also, as pressure increases, the flame comes nearer, and therefore a similar law, that is the same law R is equal to APN, can also be used to determine the burn rate of composite propellants. Now, depending on the value of n, the effects of pressure are modeled, but what is the value of A? A will depend on the size of ammonium perchlorate particle size, maybe the activation energy of the endothermic reactions, and maybe some of the compositional aspects like initial temperature of the propellant. As the initial temperature increases, I find that the denominator decreases and R increases. Therefore, the effect of the initial temperature, maybe the activation energy, maybe the ammonium perchlorate particle size, AP size, and all are embedded in A. Therefore, we can conclude therefore that the same law R is equal to APN, which described the burn rate of double base propellants, is also used, can be used for composite propellants, and therefore the burn rate can be expressed in this particular form. Very simple, but very illustrative, and we must be able to write such expressions for any system and do a problem. Maybe wood smoldering, maybe carbon, or maybe some charcoal burning, such type of models are possible. Therefore, let us summarize it again in terms of this slide. We said we had a flame zone at a distance x star away, then we had two zones like premix zone and this, and we got the expression for R, and let us now go back and examine the value of R. How should it change with pressure? Could I wrap this off? Is it clear to each one of us? Now I would like to use that equation and plot the value of the burn rate, logarithm of burn rate versus logarithm of pressure, because we said, well, burn rate for composite can also be described by the Philae equation or the Saint-Roberts equation, which is R is equal to APN. We said, well, R with this as per this equation is like this, but if I operate at low pressure regions in this particular range, let us say less than some threshold value, let us say P star, less than some value, I have to still determine this value. What happens at low values? Maybe AP will decompose, but then the hydrocarbon vapors are coming, and what happens is the rate of decomposition at low pressures is somewhat limited by the kinetics. Why kinetics? We always write Q dot chemical is equal to maybe A P to the power n exponential of minus E by RT, and this is what we said is small q dot chemical per unit mass over here, and therefore at lower pressures I have lesser amount of energy getting liberated, or this becomes a controlling parameter because this fellow still generates vapor but this fellow is missing, therefore this is something which is controlling. Therefore at low pressures I can say, well, in this case chemical kinetics or AP decomposition controls. When I talk of higher pressures, the diffusion is independent of pressure. At higher pressures I am getting copious amount of this coming out because the reactivity has increased, but the mixing of gases is independent of pressure, and therefore mixing gets controlled, and therefore in this zone I have something like mixing controlling the final diffusion flame. All what I am trying to say is, over normally I would get the same N over the region, this is what I was expecting, but the phenomenon is changing. At low pressures I get premixing or premixed flame dominating, or this is the limiting factor which controls the final temperature, whereas at very high pressures diffusion is less, and therefore since it is less it becomes the controlling factor, because this is available to you but this is not allowing the availability to get back into the final temperature, and therefore I say it is mixing control. In other words, if I were to again replot this, I have a region in which I have premixed combustion controlling, and at higher pressures I have something like diffusion mechanism controlling, and this pressure is of the order of something like little bit more, maybe something like 15 atmospheres or so. And what happens is, whenever it is premixed control I have a higher value of N because it goes as P to the power N what is controlling, and if it is diffusion control I have something like N which is lower. Therefore for composite propellants what happens? It is different from double base propellants in that if I were to plot the value of logarithm of burn rate versus logarithm of pressure, I have something like high value here, high value, smaller value of N over here, or rather the burn rate goes something like this. Whereas what did we have in that case of double base propellant? It was just the opposite. We had at higher values we had a steeper value something like this, and at lower value we had this. In fact we had something like this in the case of double base, whereas in the case of composite it is the reverse, and we have small n at the lower pressures and higher value of N at the lower pressures and smaller value of N at higher pressures, higher value of N at lower pressures. I think this distinction must be clear. But normally most of the rockets we operate at pressures in excess of this, and therefore we will say that N typically is around 0.3 to 0.25 to 0.35, whereas in this region wherein n is nearer to something like 0.4 to 0.5 we have premixed combustion, n between this is what we operate and it is diffusion dominated. I think I showed this in this particular slide wherein I said at a pressure less than a threshold value I have premixed a higher value of n followed by diffusion wherein I have a lower value of n. I think this is about it, and now if this part is clear I can go to the choice of n which is necessary for me to give the particular criterion of how I choose a propellant. What must be the value of n which gives me stable burning? Can I say I have understood the burning rate laws? Now if I were to question you before getting into this, what should be the burn rate law for a composite modified double base? I know for a double base the burn rate law, I know for a composite the value. We can say composite modified double base should incorporate both these features and give something like average of these two. In other words, composite modified double base will give a value of n which is slightly lower than for double base. For double base it is all premixed, therefore n is high for double base. For composite at the regions of interest n is low, therefore for composite modified double base n will be smaller than for double base. If I were to consider something like nitramine propellants, well in nitramine propellants I had HMX, I had binder which were mixed together, both of them are premixed and therefore n should be high. That means in the burn rate law R is equal to AP to the power n, n is higher for nitramine propellants, for CMDB it is less than double base but higher than for composites. I think this is the way one should take a look at it. It is possible to do the same type of analysis for this and come to the same conclusion. I think let us keep it in mind, we should work out some numerical problems for burn rate and put things together. But what we have done is for double base, yes we looked at the evolving layers like fizz zone, dark zone and also the second luminance zone, whereas for composites we use the simple Hermann's model wherein we talk of a flame standing away from the surface by a standoff distance. We also know what this standoff means, right? When a gas comes it takes some time for things to chemically react and form a flame. I would now like to ask myself, as I was telling you, if I have R is equal to AP to the power n, can I formulate a law which says n should be small, n should be greater, what should be the value of n which I want? Should I have n equal to infinity, should I have n is equal to 0, what is the value which will give me a good burning in a rocket? Therefore for that let me go ahead, let us say I now come back to a system of a solid propellant rocket. I tell myself, well this is the propellant what I have in a rocket as it is, this is my burning surface area SB. In other words I have, if I take a section over here, this is my surface, this is my burning surface area SB meter square, and this is where the burning takes place and gas is getting released and the gas gets pushed out through the particular nozzle. Let us put some numbers down. We will call rate at which mass is getting generated from this surface area as equal to m dot generated, m dot g. The rate at which gases are leaving the nozzle we will call it as m dot n. Can I write an equation for the dependence on m dot g and m dot n from this? Let us consider the case wherein I have a certain volume, let us say this particular volume over here is V, let the pressure in this volume be P, let the temperature of the gases be T. How do I write an equation? mass gets generated over here m dot g, it leaves the control volume of this volume at a rate m dot n. What is the equation I have? Mass balance, if I have it to write, what will I get? Yes. M dot g, yes, you are telling it should be m dot g minus m dot n, gas leaving, should be the rate of accumulation of gas in the particular volume of the chamber. What is the value of m from gas equation? We have PV is equal to mRT, the pressure is P, small p, the volume is V, the temperature is T, therefore m is equal to PV by RT. Therefore, I can now write d by dt of PV by RT is equal to mass of gas which is generated at the propellant surface by burning minus m dot n which is leaving through the nozzle. Is it okay? Let us simplify this term before I come into these particular terms. How will I simplify this particular term? What are the variables? Temperature is a constant, flame temperature. Pressure, I am considering a particular value of pressure, it could vary. As the propellant regresses, the volume varies. Therefore, I have two variables, pressure and volume. Well, the flame temperature is a constant. Therefore, for temperature being a constant, R anyway is a specific gas constant, it is constant. I can write this equation d by dt of PV by RT one over RT into V of dP by dt plus P of dV by dt. Is it all right? Now again I simplify this, I write it as V by RT of dP by dt plus P by RT of dV by dt. What is P by RT equal to? Let us take a look at the gas equation. PV is equal to MT, PV by RT is equal to mass by volume, which is the gas density. I can write this as equal to V by RT into dP by dt plus density of the gases into dV by dt. Okay. What is dV by dt? What did we tell ourselves? The rate at which the volume is increasing. And what is the rate at which volume is increasing? The burning surface area is SB, regression is by R, therefore dV by dt is what? Yes, dV by dt is equal to burning surface area into the propellant burn rate, so much meter square into meter per second is the burn rate law, meter cube by second, this is dV by dt over here. Let us follow this. What is it I am telling? In 1 second the distance would have been moved by R, therefore the increase in volume dV by dt is R into SB for 1 second, or dV by dt is equal to SB into R. Okay. Therefore, now I can rewrite the equations in a controllable manner as RT by V, was it the value? Yes, V by RT into dP by dt plus I have the value of rho p into dV by dt, which is equal to rho p into burning surface area into propellant burn rate. Let us make sure it is correct, is equal to what? M dot generated minus M dot nozzle, what is leaving. Is it okay? V by RT dP by dt rho g, yeah, you are right. What we had here was rho g over here, we multiplied it by SB into R, very good. What is the value of M dot G in terms of pressure or in terms of burn rate? Yes, burning surface area into R into rho p, because SB into R tells what is the volumetric rate at which it is going, multiplied by the propellant density is the mass at which it is getting generated. Let us be very clear, which is equal to SB rho p into A p to the power n, where R is equal to A p to the power n, I use the law. Now what is the rate at which mass is leaving the nozzle? We have been doing it all along. C star we used solid propellant property, that is m dot n is equal to Pc AT, now I am calling P as the chamber pressure by C star. This was the definition of C star. That means we said C star is the transfer function between chamber pressure and mass flow rate per unit throat area, and therefore let us just substitute it and get the answers what we are looking at. So I substitute this again, I get V by RT is equal to, let me make use of this space now, is equal to SB rho p into AP to the power n minus P into AT by C star. I can write R here also as AP to the power n, burn rate law, and what is it I get? Let's put it together. Now I get dP by dt is equal to RT by V into SB into AP to the power n into rho p minus rho g plus minus P AT by C star. All what I have done is I brought rho g here because it is a minus sign now. I have SB into AP to the power n, and this is my value. That means I have dP by dt, I take RT on this side over here. Is it all right? Please check it. Now I want to know what happens under steady conditions. By steady conditions I mean the pressure with respect to time is a constant, pressure does not change, therefore dP by dt is 0, therefore I get this term must be equal to this term, or rather I get the value of SB into AP to the power n into rho p minus rho g is equal to P AT by C star. If we were to call this steady value of chamber pressure, which is actually the steady equilibrium value, as equilibrium pressure, the value of equilibrium pressure P equilibrium is equal to, I take n on this side, I get therefore SB into A into rho p minus rho g into C star divided by AT, and now I take here 1 minus n, therefore this becomes 1 over 1 minus n. please check whether it is all right. I take P on this side, it becomes P into 1 minus n, and I still retain S A rho P minus rho G, and I take C star upstairs over here and AT downstairs over here, and this becomes my equilibrium pressure. What is it I am telling? All what I am saying is when I am burning a propellant, whatever be the configuration of the grain what I have, if this pressure is constant, the equilibrium pressure is given in terms of the burning surface area, the pre-exponent A, the difference between propellant density and this, the C star of the propellant divided by AT is gives me the value of the equilibrium pressure. Let us take a look at this. Normally the gas density will be very much lower than propellant density. In fact, had I neglected the gas density, I would have got this expression to be even simpler. I would have got this to be equal to SB into A into rho P into C star divided by AT to the power 1 over 1 minus n. This should have been the value of my pressure equilibrium. This is a particular case because this will be around 1,000th of the normally the solid has a much higher density than a gas. Therefore, what can I draw some conclusions from this? Now I tell myself, if please be attentive, I think you should be able to discuss this point. If n has a value near 1, what will happen to this equation? If n has a value of 1, well, I have infinite pressure, it is just not possible. If n is around 0.995, very near to 1, then I have a very large exponent, and small perturbations or changes in this will give me a high value. Therefore, a value n near 1 is not acceptable. That means n must be as small as possible, and that is better because I have a much smaller value, and therefore any changes in burning surface area while it is burning, some changes in the gas density while it is burning, some changes in C star or throat area should not lead to an explosion and getting a abnormally high value. Therefore, we tell ourselves that one of the qualities required in the burning rate of a propellant R is equal to AP to the power n is n must be a small number, a large number is just not acceptable. And we say yes, for composites around 0.3, 0.25 to 0.4, well for double base it is around near to 0.5, 0.4 to 0.5, therefore maybe composites are a little more better than double base propellants. Well, having said that, I can also use the same thing in a slightly different format. I can look at the value of the value of n which is desirable. Let us do it graphically. It will take me just a couple of minutes, let us just do it together. Let us say I have something like mass generation rate of propellant as a function of pressure. We said m dot g is equal to APN into SB and all that, that means mass generation rate is equal to SB into AP to the power n, therefore it will go like this, right. Here I must multiply by the density of the propellant rho P. What is the rate at 0 pressure? It must be 0, therefore I should bring the curve down. If I have n which is greater than 1, well this will be my shape. If I have n less than 1, what will be the shape? Yes, we must learn all this, we must be able to do these things. That is why I think this the basic aim of this subject is to be able to put things together. N less than 1. Now what is the value of m dot n? M dot n is linear, P AT by C star for straight line, this is m dot g. Now I am also putting m dot n on it. Same thing, I also have a line for m dot n. I should not have written R here, I should have written m dot g and m dot n, right. Okay. Let us take a look at these. What is this point wherein both are equal, steady state, P equilibrium? What is this point, P equilibrium? Right, and we know the expression for P equilibrium. We have just derived it as saying SB small a into something like C star divided by AT to the power 1 over 1 minus n. Now let us examine this particular point. Supposing by chance as the motor is functioning, there is a small diversion in pressure, pressure slightly increases. If pressure slightly increases, the mass generation rate increases, pressure further increases, it goes like this and it explodes. If pressure slightly falls, the mass flow through the nozzle is higher, therefore more mass flow rate compared to mass generation, pressure comes down, it comes down, it comes down, it extinguishes. Therefore when I have n is greater than 1, I cannot get equilibrium, the motor either quenches or it explodes. Therefore n greater than 1 is not possible. You cannot have a propellant because it will not usable, I will say, right. Let us come back to this and examine this again. If there is a slight increase in pressure, what is going to happen? The pressure has increased, the nozzle flow rate has increased, therefore the pressure again comes, it comes back to this and it is stable at this point. If the pressure falls slightly, if the pressure has fallen, mass generation rate is higher, it gets back to this point, therefore this becomes my stable operating condition. Therefore now I am very clear, n must be very much less than 1 and that is how it is preferred. We learned how to do this using these two plots. We also learned how to do this using the equations wherein we had the expression raised to the power 1 minus n, and this is how we decide the choice of n. I will continue with this in the next class, but what we did in this particular class was we derived an expression for the burn rate of composite propellants using the standoff distance x. We found that it is still modelable using the Saint-Roberts law, namely R is equal to AP to the power n. We related it to a rocket and we said, well, n must be very much less than 1. In the next class we will look at the temperature sensitivity of R. We will also look at some other parameters which are important for R and then go to designing a solid propellant rocket. And what do we do in a design? We have to have a particular burning surface area. It becomes a simple geometric problem and this is what we will do in the next class, right. Well, thank you then.